And now I want to discuss the concept of a functor, which is the key thing that we use to relate different categories. C and D be categories. So a functor, let's say F from C to D, consists of two ingredients. So firstly, a rule giving an object FA of the second category D for each object A of C. Okay, so this first ingredient is a way of converting objects of C to objects of D, if you like. And then nextly, a rule giving morphism FF, morphism in D from FA to FB. And that's for each morphism F from A to B and C. Okay, so this second thing is a way of converting morphisms in C to morphisms in D. And these things are supposed to satisfy two axioms. Okay, so the first thing is that F has to preserve identities in the following sense. Okay, so if we've got some object A of C, then it has an identity morphism, id A from A to A. We apply F to it, we get a morphism from FA to FA, and that should just be the identity morphism of the object FA and D. So that says that F preserves identities, and the second thing is that F has to preserve composition. So more precisely, if I've got a pair of composable morphisms in C, okay, so then there's two things we could do. We could apply F to the composite. Okay, so that's we do the composition in the category C, and then we apply F to get a morphism in D. Or alternatively, we could apply F to little f and little g separately, and then compose them. So this is two different morphisms in D, or two morphisms in D from FA to FC, and those are required to be the same. So this axiom C says that F preserves identities. Axiom D says that F preserves composition. And so that's kind of complicated, but the basic idea is that almost always, if you've got two categories C and D and some procedure for converting objects of C to objects of D, then it almost always works out that you can regard it as a functor by specifying the action on morphisms in an appropriate way. So we'll have some examples there. Let's just give the most basic, most basic example, but in some sense the most interesting example we've seen so far. We've got the functor pi0 from top to set. So here top is the category of topological spaces and continuous maps, and sets is the category of sets and functions. So pi0 of a for any space X, we've got pi0x is the set of path components. So we've discussed a whole bunch of stuff about that in earlier videos and things. And pi0f, let's say, given f from x to y, we put, well, we're supposed to have a map from pi0x to pi0y. And we kind of did this already. We just used slightly different notation. Before we called this map f lower star. Let's just recall that this is kind of basically defined by f lower star of square bracket a is square bracket f of a. And the kind of real point about this definition was just to check that it's well defined, that if square bracket a is the same as square bracket a prime, then square bracket f of a is the same as square bracket f of a prime. So this rule is actually giving us a well-defined function. But once you believe that, that's then we can define pi0f to be equal to this f lower star. And then we want to say this is a functor. To say it's a functor, we need to check that pi0 of the identity is the identity, and pi0 of g composed with f is pi0 g composed with pi0 f. And those are actually, that's just the lemma that we proved at the end of the last video. So that's one example of a functor. And then we'll have a few more examples in a minute. So here's another example. So given a metric space X, define Tx to be it's just the same set X, equipped with the metric topology. So here, X is an object of the category of metric spaces. Tx is an object of the category of topological spaces. So that's a way of converting objects of one category to objects of another category. But to promote it to a functor, we need to say what's its effect on morphisms. So we've got a morphism in the category of topological spaces from x to y. That just means it is a continuous function from x to y. And then we just define Tf is equal to f. So morphisms in the category of metric spaces are just continuous maps. Morphisms in the category of topological spaces are just continuous maps. So f, this original f, we can regard it as a morphism in top or as a morphism in metric. It's just the same thing. So this is kind of, on one hand, this sort of feels a bit funny. It feels kind of so simple as to be confusing in a sense. Because there's not really anything going on. But the place where anything is going on really is just in the fact that we defined this metric topology and we had to prove it was a topology. That's where all the content is going on, just in the basic definition of a metric topology. And then all the other ingredients are just somehow kind of automatic. And that's a fairly common sort of thing that happens in category theory. When you define a category or you define a functor, many of the ingredients are just sort of automatic and nothing really is happening. And there's just kind of one ingredient somewhere where all the content is involved. So that's a factor. So let's have another example, a slightly different character. For a set X, let's put Px is just X cross Z. And remember what that means. That's just a set of pairs x comma n. If x is in x, n in z. Okay. So we want to regard this as a functor. So of course, x was just a set, px is just a set, so this is going to be a functor from the category of sets to the category of sets. But to make it a functor, we need to say what it does on morphisms. So given a function f from x to y, we need to define pf from px to py. Now we need to define a functor like this. You need to define a function, pf, and well, what's it going to be? So typical element of px is just like x comma n, so we need to give a formula for what this is going to be. And this has to be an element of the set y cross z. So the first component has to be an element of y. What element of y could it possibly be? There's really only one element of y that we can produce out of these ingredients. What we have to do is just take the function f from x to y and apply it to x, right? So we've got f of x here. Okay, that's the only element of y that we know how to produce. And then the second component has to be an integer, and the simplest way to produce an integer is just to use this n that we've already got. Okay, so that's going to be our definition of pf. Okay, so we need to check that this is a functor. So we apply this to, say, a composite G composed with F, so then this is going to be, by definition, G composed with F applied to X and N, which is G of F of X, comma N. And it's pretty easy to see that this is the same thing as PG of PF of X, comma N. So that's what we need to show that P of G composed with F is the same as PG composed with PF, which is the second axiom for a functor. And then the other axiom is just that it has to send identities to identities, and that's also, well, that's just completely obvious here. So this gives us a functor P from sets to sets. Now I want to give a couple of algebraic examples. So let's recall the category of abelian groups. Okay, so and so we're going to write abelian groups always with additive notation. So the group operation is just going to be written as plus. The identity element is going to be written as 0. So let's just record what that means in terms of the morphisms. Ab A, B is a set of f from A to B, such that f of 0 is 0. F of A plus A prime is f of A plus f of A prime. The homomorphisms of abelian groups, they have to send 0 to 0 and preserve addition. Okay, so now we want to define a certain functor, which I'm going to call D. So dA is just going to be the double of A as 2A, and it's a set of A plus A. So this is a certain subset of A, the set of things of which can be written as A plus A for some A. Okay, so that's yeah. So it's easy to see that this is a subgroup. So we can regard it again as an object of the category app. Now, okay, now let's suppose we've got some homomorphism from A to B, and U is an element of DA, which means that U can be written as A plus A for some A. Then F of U is F of A plus A, which is F of A plus F of A. And because this is the sum of something with itself, we see that this is an element of DB. So it means that we can define df from dA to dB by dA just by restricting the integral map f. So we just restrict f, so df of u is just the same thing as f of u. But I mean, the point is that the point to check it, we have to check this f of u really lies in dB, but that's what we just did here. Okay, so we've got a function like this. Okay, and then from this, it's easy to see that d of the identity is the identity, d of g composed with f is dg composed with df. So this functor d from ab to ab. So examples of what this does, I mean, okay, if you look within the group Z mod 2, well, the double of anything in Z mod 2 is 0, so d of Z mod 2 is 0. If you look in Z mod 3, well, Z mod 3 is kind of 0, 1, and minus 1 mod 3. D of 1 is minus 1, D of minus 1 is, sorry, twice 1 is minus 1, twice minus 1 is 1, so you get everything. So D of Z of mod 3 is just Z mod 3 again. So that's a functor D. And we can also define a related functor Q. So QA is just going to be the quotient, A mod dA. Remember, we're dealing with abelian groups here, so there's no issue about normality. All subgroups are normal. So you can always just take a quotient. So the elements of this are cosets, right? So this is the set of cosets, A plus dA, A lying in A. And then we want to try and define QF like this. Okay, so so a couple of things we need to check here. I mean, so I want to define QF by this rule on cosets. You've got a coset A plus dA, then you just apply F to your A and FA plus dB. So we need to check that this is well defined, right? The same coset could maybe be described as A prime plus dA, and you need to check you get the same answer on the right-hand side here. And also you need to check that this queue sends identities to identities and preserves composition. And so none of those things are difficult, and they're spelled out in the notes. I think I'm not going to go through them in this video. But this is giving us we find that Q is another functor from ab to ab. Okay. So that's a decent supply of examples of functors.